So, if we're looking at the graph of x squared minus 9, it looks like this. It's a quadratic. If I look for where x is approaching 5, if I type in x equals 5 over here, it'll put me a vertical line so I can kind of picture that. We were drawing those vertical lines in yesterday. So from the right and from the left here, I've just got a solid line. So I'm just approaching that point right there, that intersection point. And its y-coordinate right there is 16. All right. So the very easiest way to do a limit algebraically, if you know the equation, is just to plug the number in. So you can see here, if I just take this 5 right here and plug it in, I would do 5 squared minus 9. That would give me 25 minus 9, which is going to give me 16, which is what I saw on the graph as well, right? Because what we see here should also match up on the graph. So this method is called direct substitution. So if you can just plug in a number and get an answer, then that is your answer, right? So that's the first thing you want to try every single time. So if we look down here, and let's say I got to remember you guys are writing these down, so let me slow down a second so you guys can get that down. So, so go ahead and copy those 2 examples for me right there. So if we have a problem like example 2, we got the limit as x approaches 2 of 1 over x plus 2. All you're going to do is just plug in 2 plus 2. That's going to give you 1/4, and that is your answer. Now, it can happen like we're going to see on example 3. We got the limit as x approaches 2 of 1 over x minus 2. So if we plug in 2 minus 2 here, we're going to get 1 over 0. What is 1 divided by 0? It is not 0. 0 divided by 1 is 0. It's undefined. So if we see this happening where we've got a number divided by 0, this is going to tell us the limit does not exist. Yes. So what usually happens at those cases is you have a vertical asymptote. And so from each side, it may approach infinity or negative infinity, or sometimes it may actually, they both approach infinity where you could call it infinity. But those are technically limits that do not exist, so you can just go with does not exist for that. For what we're going to do, I probably won't ask you to tell me positive or negative infinity unless it's from a graph. When you guys get into calculus, we'll get into doing that a little bit more in depth. But if you have a number over 0, just go ahead and say that limit does not exist if we're doing this algebraically. Now, there is a time when direct substitution fails. So you want to write this down. This will be important. Direct substitution fails when you get 0 over 0. Okay, a number over 0 tells you the limit does not exist. So if you get 7 over 0, 1 over 0, negative 15 over 0, that tells you the limit does not exist. If you get 0 over 0, that does not tell you anything. It tells you that you need to do some more work, because if you get 0 over 0, it is possible that the limit does not exist, but it is also possible that that limit does still exist. This 0 over 0 has a name. It is called the indeterminate form. Same problem. Yeah. Okay, so you always want to try direct substitution first, because if direct substitution works, that is your answer. But if you, as you can see in this case, now I'm going to do something here that is mathematically incorrect, but I don't think you guys will mind. Technically, nothing can equal 0 over 0. I'm going to do a string of equal signs like these are equal to each other. And technically, nothing can equal 0 over 0 because it's the indeterminate form. It means you cannot determine anything from it. It can't be equal to it. So if I were really being precise, I should do the limit. I should do it this way. Limit as x approaches 2 of x minus 2. Do the limit of the top, which is 2 minus 2, which equals 0. And then I should do the limit as x approaches 2 of the denominator, x squared minus 3x plus 2. I should do these separately and say that's 2 squared minus 3 times 2 plus 2, which is 4 minus 6 plus 2, which equals 0, to show that those both equal 0. That is the mathematically correct way to do it, and there's going to be, I tell you all of that to say that whenever you take calculus and we get to a part called L'Hopital's rule, you have to do it that way. But for right now, it's okay with me if you guys just plug it in like this. 2 squared minus 3 times 2 plus 2, and you get 0 over 0. Mathematically, that's incorrect to put equals 0 over 0. And it should be done like I did there on the bottom. But it's all right with me if you just, plug it in that way, have those equal signs. So when we get 0 over 0, it is telling us nothing. It's telling us that we don't know anything about this graph. Whenever we run into 0 over 0, which is going to be the majority of the cases that you're going to run into, because obviously direct substitution is really, really simple, and I don't need you to practice that very much, right? So usually when we're looking at these graphs, we're looking at the interesting points, the places where you have something happening, maybe a vertical asymptote, maybe a hole in the graph. So we're not usually looking at points where it's just direct substitution. So we're going to have several strategies that we're going to use to figure out these limits. So the first one we're going to look at, and we're going to do the same problem. So here are some strategies that we can use if we are looking at this. Yeah, I'll take it. Thank you. All right. So, and we're just taking notes on paper today, Jackson. You haven't missed too much. Only the very, very easy part. So that's good. So, Jackson, what we were just saying is that if we're trying to figure out a limit algebraically, so we're just looking at the equation and not necessarily the graph, I'm going to flip back here for a second. So what we can do is we can just plug in the number they're telling us to plug in. So like if I plug in 5 right here, I will get 16. So 16 is my answer. Here I plug in 2, I get 1/4. 1/4 is my answer. Now, right here I got 1/0, which is undefined. So that tells me that the limit does not exist if that happens. But there is a way that direct substitution, just plugging in that number, is going to fail. And that is when you get 0/0. So on this equation right here, we have plugged in 2, and we end up getting 0/0. And that's called the indeterminate form, and it means we're going to have to do something else to the problem. So the first strategy that we're going to try, and the one that works on this particular problem, how to make that, is we're going to factor and cancel. You don't have to recopy this. This is the same problem that we were doing up here, example 4. So obviously, right here, the numerator will not factor. Also, I should also say this. For notation purposes, and notation is really important for me because when you guys get to calculus, I keep saying that when you get to calculus, some of you may never get there, it's okay if you don't, but even if you're not taking it with me next year, you might get to calculus eventually. And the notation is really important whenever you're showing this, especially if you're taking AP, because there's a written part of the test that you have to have your notation right or you don't get points on. And if you're taking it in college, your professors are probably also hand grading and could possibly be pretty picky about notation as well. I never had many professors that gave tests that were not just on paper in college. Of course, it's been a while. But, I mean, the technology was there for them to test this online. Not as good, but you're probably going to have some paper tests if you take calculus, I would imagine. Right here, we want to do limit as x approaches 2. We do not get rid of the limit notation until we're plugging in a number. So you got to keep that limit notation until you're actually plugging in 2. Now, I tried to plug in 2 up here, but it didn't work. So now I'm having to back up and try a different strategy. So numerator will not factor. We just leave it x minus 2. The denominator here will have an x and an x. And this one's going to be a minus 2, minus 1. Now, what do you guys notice can happen right here? This x minus 2 can cancel with this x minus 2 in the denominator, which is usually what's going to happen in a problem like this because we can't really do it otherwise. Hello? Sure, thanks. Bye. Grace, that's you. I'll keep recording. All right, so all we have to do, once something cancels, now we have the limit as x approaches 2 of 1 over x minus 1. And now, once something cancels, you're probably going to be able to just plug in the number. So if I just plug in the number, now I'm plugging in 2, so I'm not going to use limit notation anymore. I'll have 1 over 2 minus 1, which is just 1 over 1. So I get 1 for my answer. Yes. When you plug the 2 in. So if you still have x's, you still need limit notation. But when you take the 2 and you plug it in where the x is at, that's when you stop using the limit notation. Or whatever number you have there. Okay, questions? All right, let's try another one. So we've got limit as x approaches negative 3 of x squared plus 5x plus 6 over x to the third. So x to the third, x plus 3. Okay, now we should always try direct substitution. I'll be honest, I often forget to try direct substitution. Sometimes we're going to do a quiz on this section and not a test, so I'm not sure. Well, we'll have some of this on there, though. When I used to give a test, when I give a test on this, one of the most missed questions is a question that looks like this, but it's actually a direct substitution problem. So like it looks like this, but instead of x approaching -3, it might be like x approaches 2. And it looks like you need to factor and cancel and plug something in, but it doesn't factor and then they don't know what to do. But it's because it's just a direct substitution problem. So every time we should be plugging in direct substitution to check that first. So if I have -3 squared plus 5 times -3 plus 6 over -3 plus 3, that is going to give me 9 minus 15 plus 6 over 0. And 9 minus 15 plus 6 is 0. So 0 over 0. This is never your answer. You should never circle 0 over 0 as your answer, right? This is 0 over 0 tells you you're not done yet. You need to keep going. So if you find yourself circling 0 over 0 as your answer, then you've done something wrong. So what we need to do here is we need to factor this. So we're going to do the limit as x approaches -3, and we'll factor that numerator. Let's see, Blaine, how will that one factor? We got multiply to get 6. Add or subtract to get 5. 3 and 2. So we have plus 3 plus 2. And let the denominator help you factor a little bit too, because it's usually there's going to be something canceled for most of these. Not always, most of the time. So x plus 3, that's going to cancel. At this point, I just have the limit as x approaches -3 of x plus 2. And I'm just going to plug in -3, -3 plus 2. I can drop limit notation because I'm plugging in -3 here. And I will get -1. That's my answer. What's happening right there at -3? If I think about this graph when we did rational functions, where I've got that -3 is the value that gives me a 0 right here. What is that going to look like on the graph? It's a hole in the graph. So like if you graph this on Desmos, if we were to graph this, and we were looking at -3, if I look at it, it looks just like a line. It looks like you should have an intersection there. But when you try to click on it, it is actually undefined at that point. So you just have like a single hole in the graph right there. And so a lot of times what you're looking at is you're looking at places where you have a hole in the graph for these. All right, let's try this next one. So we got limit as x approaches -6 of x plus 3 squared minus 9 all over x plus 6. So direct substitution every time you need to try it first. It's okay with me if you do this part in your head, but you need to do this part. So I'm going to write it down so we are thinking about doing it for the purpose of showing you what to do here. So you would end up with -3 squared minus 9 over 0. That is going to be 9 minus 9 over 0, which is 0 over 0. Most of them you're going to get are going to give you 0 over 0 because we're looking at those difficult points, right? So that's why a lot of times people quit checking for it because it ends up being 0 over 0 so often. But we don't want to quit checking. So, in this case, I can't cancel anything. And I can't really factor because I've got that x plus 3 squared. So what I'm going to have to do here first is I've got to multiply this out first, then see if I can factor and cancel. So we're going to keep that limit notation. And then here I can square double square. So I'll get x squared plus 6x plus 9 minus 9 over x plus 6. What happens with those 9s right there? They'll cancel out. So that leaves me x squared plus 6x over x plus 6. What can I do to factor that? What did I hear there? Factor out of x. So you can pull just like a greatest common factor out here. So x times x plus 6 over x plus 6. And so now that things are factored, those x plus 6's can cancel. We will just have the limit as x approaches -6 of x, which if we just plug in our -6, we're just going to get -6. There's our answer. Okay, questions on that one? All right, try this one on your own. Hey, did Luis? Pretty happy as I walk around because not too many of you have got hung up on this one. Lots of you have got the answer. What's the first thing we do? Check direct substitution. And when you do that for this problem, look at that denominator. I'm going to get 2 plus 3. So is this going to be one where I need to factor? No. So I got 2 squared minus 4 times 2 plus 3 over 2 plus 3. So I got 4 minus 8 plus 3 over 5. And that's going to give me -4 plus 3 will give me -1/5. So this is just a direct substitution. I saw a couple of you trying to factor. The problem is when you factor, you got an x minus 3 and an x minus 1 over x plus 3. Nothing cancels, but it doesn't need to because you don't have 0 over 0. You could just use direct substitution there. So you guys did a good job on that one. All right, so factoring and canceling, that is one of the big strategies that we're going to use. Let's look at some other types where we're going to need a different strategy. Okay, so the second strategy that we're going to use is we're going to rationalize. So this goes back to, we did a lot of this back when we were doing like imaginary numbers and we were rationalizing. We didn't usually have an x with it. We usually had something like 3 over 7 plus the square root of 3, something like that. And usually that root was in the bottom, and I had you guys rationalize it so you didn't have that square root in the bottom. How did we do that? How did we get rid of the square root in the bottom for that? Almost. 7, or what'd you say? Minus square root of 3, right? We did that on top and bottom because when we did that, 7 times 7 was 49. 7 times negative 3 was a negative 7 root 3. Here we got a positive 7 root 3, so those cancel. And then we got minus 3 there on the end. So we got a whole number there. Whenever we did that, we would have 3 times 7 minus root 3 over, we're going to have 49 minus 3, so 46. So that was our rationalizing, right? So we're going to do something similar over here. But we are going to not necessarily rationalize the denominator. We just are going to rationalize whichever side has the square root in it right now. So if I plug in 1 right now, I've got square root of 1 minus 1 over 1 minus 1, and the square root of 1 is 1, so this just gives me 0 over 0. All right, so direct substitution fails. We're going to have to do something else. So what we want to do here, we're going to take that square root of x minus 1 and our x minus 1. We're going to start off by putting both of those in parentheses because we're going to have to multiply them by some stuff. And so we are going to multiply by the square root of x plus 1. In this case, you're actually rationalizing that numerator. You want to get the square root out of the numerator. And here is why this is good. So when I multiply this together, square root of x times square root of x is going to give me just an x. Then I will get a positive square root of x. I'll get a minus square root of x. And I'll get a minus 1. And in the denominator, don't multiply those together. Keep them factored. This is a general rule. You don't want to do that. And hold on to that limit notation because you have not plugged in the 1 yet. And I normally would not write this particular step right here because what happens with the positive square root of x and negative square root of x? They're going to cancel out. So what I really have here, I usually would go ahead and skip to x minus 1 over x minus 1 square root of x plus 1. And why is that good? X minus 1s, they can cancel, which means at this point we have the limit as x approaches 1 of 1 over the square root of x plus 1. And so once you have something cancel, you want to try to plug in that number. And if we do here, we got 1 over the square root of 1 plus 1. Square root of 1 is just 1, so that's 1 plus 1. And we get 1/2. Okay, questions? Let's try another one that's a little bit tougher. So this time we've got, we're plugging in 5, so let's check it to make sure we are in fact getting indeterminate form. That's going to be square root of 4 minus 2 over 0. Square root of 4 is 2. 2 minus 2 is 0. So we get 0 over 0. I'm writing it down each time just because I want to demonstrate to you very clearly what we're doing there. But if you're doing that in your head, that's fine. You don't necessarily have to write that down. This just tells us we got to do something else. So what we want to do here, so we got square root of x minus 1 minus 2 over x minus 5. Start off, put yourself some parentheses, top and bottom. So we need to multiply by the conjugate. That's a fancy word for what we were doing on the last problem. I don't know if I said it. Which is square root of x minus 1. Don't change what's inside the square root. You only change this minus sign right here to a plus 2. So that sign right there is the only one that changes. Everything else about it stays the same. And then in the denominator, we would also multiply by square root of x minus 1 plus 2. So when we do this, the reason we chose the conjugate is so we would have a difference of squares. So those middle terms would cancel out, right? So we're going to have square root of x minus 1 times square root of x minus 1. We'll get x minus 1. Then the outside terms is going to be plus 2 square root of x minus 1. The inside terms are going to be minus 2 square root of x minus 1. I'm just not even going to write that because they're going to cancel each other out, right? And they will every time unless you've messed up your conjugate. And then we got to do negative 2 plus 2, which is going to give me a negative 4. So we got the limit as x approaches 5 of x minus 1 minus 4 over x minus 5 times square root of x minus 1 plus 2. Right? You guys should be able to see what's going to happen right here when we put that negative 1 and negative 4 together. What do we get? Negative 5. What's going to happen with it? It's going to cancel with this in the denominator. I'm going to write that step, but if you skip over it for me, that's okay with me too. So we would have x minus 5 in the top. And we would cancel the x minus 5 there. So we're left with 1 over square root of x minus 1 plus 2. Typically at this point it's okay to plug numbers in. So we're going to have the, oh wait, I'm plugging numbers in, so I'm not going to use limit notation. I'm going to do 1 over square root of 5 minus 1 plus 2. So that's square root of 4 plus 2, which is going to give us 1/4. Questions? All right, I got one more that's a little tougher that we're going to do with rationalization. And then we got 2 more strategies. Hopefully we can get through pretty quick. So you'll have a little time to work on this in class. All right, so for this one, we got the limit as x approaches negative 2 of square root of x squared plus 5 minus 3 over x plus 2. So, if it's all right with you guys, I'm going to plug this in my head. Negative 2 squared is going to be 4, plus 5 is 9, 9, square root is 3, 3 minus 3 is 0, negative 2 plus 2 on the bottom is 0. We're getting 0 over 0 here, right? So, I'm going to write it down because I know this problem is a little bit longer and I don't want it to take up 3/4 of a page. But if you plug in plug in negative 2, you're going to get 0 over 0 for this one. So we need to rationalize. We'll put parentheses here. And then we are only changing this sign right here. Nothing inside of the square root, just that sign between them. So we've got square root of x squared plus 5 plus 3 here. And so when we multiply this together, the square root of x squared plus 5 times the square root of x squared plus 5 is just x squared plus 5. Then we would have to do the outer terms, 3 times square root of x squared plus 5, and the inner terms, but what happens with those? They cancel, and they should every time if we've chosen the conjugate correctly, right? So those cancel. I'm not going to write them. That just leaves us the last terms. So negative 3 times 3 gives me a negative 9. And don't multiply the denominator together. It is just going to make your life more difficult. So this is giving me the limit as x approaches negative 2 of x squared minus 4 over x plus 2 square root of x squared plus 5 plus 3. Now the other two, something just canceled. So that made it, from that point pretty easy. Nothing cancels here. What should we do? Okay, factor that numerator. What does it factor into? Very good. X plus 2, x minus 2 in that numerator. And in the denominator, we just keep it factored as well. And so now the x plus 2's can cancel. So at this point, we can plug in our negative 2, and we'll get negative 2 minus 2 over the square root of negative 2 squared plus 5 plus 3. Negative 4 on top. This is going to be 4 plus 5, so square root of 9 plus 3. Square root of 9 is 3, so we get negative 4 over 6, which reduces to negative 2 thirds. So that one was a little trickier because you had to rationalize, but then once you rationalize, you also had to factor and cancel. So I kind of put those two strategies together for that problem. Okay, questions about anything there? All right, we got two more. We're going to try to get through them in 10 minutes or less. All right, so let's copy down that piecewise function real quick. All right, so some that you're going to get are going to give you piecewise functions. Need to go back and type these notes. My handwriting is so terrible. while you guys copy that piecewise function down, I'm going to graph it because I think it helps to look at the graph here. I'm going to enter it as 3 separate functions, but just because it's easier to do it that way in Desmos. Okay, so if we look at our graph right here, at -2, what is our limit going to be? It's going to be that point right there. It has a y coordinate of 5, right? Because from both sides, your graph approaches those points. But if we look over here at 5, what is the limit going to be? Because 5, if I put in x equals 5, that's right here. What happens to our graph at that point? We've got a jump in the graph. So is my limit from the left the same as the limit from the right? It is not. So does the limit exist there? It does not. So let's look at how we can do this without graphing it, because you may not have Desmos on these, and these are not terrible to graph by hand, but you may not really want to, and it's quicker to do it without the graph. So if I am going to find the limit as x approaches -2 from the right of f of x. From the right, if I'm looking at the graph, from the right-hand side would be this side. -2, you can see that -2 is the point where these two functions come together, right? So from the right-hand side, you would be looking at -3x minus 1. So to do this, you would do direct substitution with that right-hand side of the graph, which would be -3 times -2 minus 1. So you would get positive 6 minus 1, which gives you 5 for that. The next one asks us for the limit as x approaches 5 from the right. So 5, again, here, in a similar manner, is the place where the middle and the bottom functions are going to meet. So from the right side is going to be where x is greater than or equal to 5. It's going to be the last function there. So we would just do direct substitution. So we would just plug in -5 squared plus 4. So we get -25 plus 4. So we get -21. There. So that's our limit from the right-hand side. Now, I just said our limit at 5, is it going to exist? We said no. But does it exist from each side? When we look at that graph, hopefully I still have here. So from each side, the limit exists from that side. It approaches -21, but it doesn't exist from both sides of the graph. So, if I have, which I'm going to skip down here to 14, it's going to ask me for the limit as x approaches 5 of f of x. And that is going to be does not exist. And it does not exist because if I do my limit as x approaches 5 from the left of f of x. So if I plug in 5 into that middle function, negative 3 times 5 minus 1, I'm going to get negative 15 minus 1, which equals negative 16. That does not match the negative 21 when I did the right-hand side. So essentially, you're just taking 5 and plugging it into both of those equations and see if you get the same number. If you get the same number, then it touches, it meets, right? If you get anything different, then it does not. You have a jump in the graph. You can still have a limit from either side, but you can't have a limit at that point. What should we do for 13 where we got the limit as x approaches 4 of f of x? Okay, we're just going to use that middle one because 4 falls between negative 2 and 5. This is not a point where we are. This is not a point where we're jumping from place to place. So we just have to plug in 4 into that equation. Direct substitution. Negative 3 times 4 minus 1. Negative 12 minus 1 gives us negative 13 for that. And then the last one for this is the limit as x approaches negative 2 of f of x. So negative 2 was our point where these two graphs meet, where the first and second equations meet. We already did the limit as x approaches 2 from the right. It was 5. What is it going to be from the left if we use that top equation? It's just 5 because that doesn't have variable, right? So since they are the same from both sides, these actually meet. We can say that that limit right there is 5. Okay, questions? So if you can plug it into both equations and get the same number, then that limit exists and is that number at that point. If you plug it into both equations and they're different, that limit does not exist at that point. Okay, I've got one more for you. Everybody's favorite, complex fractions. Who doesn't love a good fraction inside of a fraction? So, if I were to plug in 0 here, I would get 1 over 0 plus 2 minus 1/2 over 0. And that's going to be 1/2 minus 1/2, 0 over 0. So, direct substitution fails. We have to try something else. So, here what we want to do is we do not want to have a complex fraction. If we can get rid of the complex fraction, maybe something will cancel. So we can do dividing fractions easy as pie, flip the second, and multiply. Our only issue with that is that the top is not a fraction. It technically can be done that way. It's just you're going to eventually have to get common denominators, or nothing will cancel or simplify if you do that. So I'm just going to go ahead and get the common denominators here. So for that numerator, we're working on just the numerator right now. I need to multiply this by 2 on top and bottom, and this by x plus 2 on top and bottom. So that will give me 2 minus x plus 2 over 2 times x plus 2. Whenever I do that, that's just the top part. We got to keep that x that's there in the denominator, and we got to keep our limit notation. Now, I would still like to simplify this numerator here further, so I'm going to distribute that negative. That'll give me 2 minus x minus 2 over 2 times x plus 2 over x. Keep that limit notation. And what's going to happen in that numerator of the numerator there? 2's can cancel. I got positive 2 and a negative 2, so they cancel. So that gives us negative x over 2 times x plus 2 divided by x. I'm going to put that x over 1. So now I've got a fraction over a fraction. I've got everything condensed there. So when I have to divide fractions, dividing fractions is easy as pie. Flip the second and multiply. So we're going to have the limit as x approaches 0 of negative x over 2 times x plus 2 times 1 over x. And since I have x right here and x right here, I can cancel them. And that is going to give me the limit as x approaches 0 of negative 1 over 2 times x plus 2. And something just canceled. So when something cancels, that's your signal that it's probably time to try to plug in the number. So if I plug in the 0 now, I will get negative 1/4. I've had a lot of 1/4 on these notes here. Question.